Welcome back. Topic 3, Part 1, Derivation of fin differential equation. A. Fin system and heat transfer modes. First, fin is a combined conduction and convection system. That is, conduction is going through the fin, while convection is between the fin surface and moving fluid. If we define a fine volume of the fin and then apply the first law to it, the first law states that all the heat into the system equals all the heat out of the system. Therefore, the heat rate from the fin Q sub F can be calculated from the equation 2, which is heat flux at a base times the cross-section area of the fin. Second, apparently, our goal to study fin system is very clear, which is to determine the fin heat transfer rate, Q sub F, due to the increased surface area in contact with the moving fluid by first obtaining the temperature profile from a semi-differential control volume, and then apply equation 2 to get it. The first question raised is, what is a semi-differential control volume? First of all, you have learned in the past that a control volume could be a finite one if all the three dimensions are finite size, or it could be a differential one if all the three dimension sizes are extremely small. Second, the control volume could be a semi-differential one if only one dimension size is extremely small, like dx in x direction, but other dimensions are finite size, like the one in r direction or circumferential direction. Now you know what a semi-differential control volume is. The second question raised is, what assumptions are made for our fin system? A. It is at a steady state and it is stationary fin. B. The fin system has a constant fin base temperature, fluid temperature, and a constant heat transfer coefficient. C. The fin has constant property of conductivity and zero internal energy generation. D. Fin temperature only changes in x direction, the fin length direction, but it is valid only when the Biot number is much less than 1. It indicates that the internal thermal resistance in other directions than x, like a r or theta direction, is so small that there is no temperature change in those directions. Next, we plan to get temperature profile by building a fin differential equation and solving it for it. B. derive general differential fin equation. First, we define a semi-differential control volume, which is taken from a finite size over the fin, and then identify all the heat transfer modes acting on it, which is conduction on the front and the back surface area of AC, and convection on the side surface area of DAS. Next, we apply the first law to the semi-differential control volume, which is conduction in minus conduction out minus convection out plus 0 internal energy equals 0, where the system is at a steady state. Second, we apply Taylor series expansion and Fourier's law to the heat rate difference. A. The heat rate difference in x direction at the location x and the location x plus dx is represented by its derivative using Taylor series expansion. B. The heat rate Q sub x is the product of heat flux and surface area, where heat flux is represented by the Fourier's law in x direction. Third, we use Newton's cooling law to represent convection, which is the product of side surface area, heat transfer coefficient, and the temperature difference between the fin surface and fluid. Fourth, plug in equation 2 for heat rate difference and equation 3 for convection. Then yield the fin differential equation 4, where the constant K is taken out of the derivative x. By checking, it is noticed that the cross-section area AC and side surface area DAS will be determined by the fin geometries. Now we have the general differential fin equation for this semi-differential control volume. We will check 2 scenarios next. The first scenario is that the cross-section area AC is constant along the fin lengths. As a result, the side surface area DAS is a product of constant parameter and differential distance dx. Next, plug in DAS back to equation 4 and take the constant AC out of a derivative, then cancel dx. Equation 4.1 becomes the general differential equation, fin equation at constant cross-section area AC. The second scenario is that the cross-section area is not a constant along the fin lengths, but the side surface area DAS still can be represented by the product of non-constant parameter and the differential distance dx. Next, plug in ds back to equation 4, but AC this time is remained inside the derivative. Then cancel out dx. Equation 4.2 becomes equation 5.2. The general differential fin equation at non-constant cross-section area. Next, in topic part 2, we will derive the fin heat rate equation. See you next time.